Welcome back. We now have the third property, the power property. So check it out. Log base b of x to a power is the same as the power times log base b of x. This is the true power of logs. This is why mathematicians were like, we need the thing. Because this took, imagine instead of where the x is that we see here, imagine the x is the exponent, like 2 to the x equals, like I could do 4, I could do 8, let's do 6. So 2 to the x equals 6. I don't have a way to solve this. That x is going to be something ugly between 2 and 3. It's between 2 squared and 2 cubed. But I can use the properties of logs to figure it out. So this property tells me if I take, let me use a different color, the log, I'll just use regular log base 10 of this side and of this side. This property tells me I can take that exponent that was the variable that I had no way to get at and move it down up front as a coefficient. So now this becomes x times the log of 2, the log of 2 being some ugly number, equals the log of 6, also being some other ugly number. And since the log of 2 is a number and it's being multiplied to the x, I can actually divide it over. And we're going to see this in a minute. This is actually how we're going to find the change of base formula. So now I actually have an expression I can calculate for x. Very, very powerful. This was also why, this kind of thing is why we only have log base 10 and natural log, because those are the two logs that are used most frequently. And we have a nice little formula that'll let you evaluate any other log once you understand how to do the change of base. Before that, though, we have to be comfortable with our power rule. So when I have the log of something to a power, the power comes down. That's how I think of it. It powers down. So that's how we're going to see it down here in the example. But before, let me give you an example with numbers to see if you buy into it. So the log of 100 to the third power is hopefully equal to 3 times the log of 100. All right, well, let's crunch that. I know what 100 is. This is really the log of 10 squared cubed. But I know what to do with exponents like that, which is where the power property comes from. One exponent getting on the other exponent. They multiply. And now we have log base 10 of 10 to the 6th is the number 6. Now on the other side, 3 times the log of just 100. Well, I know 100, though, again, is still 10 squared. And I know this log base 10 of 10 is going to cancel out. And the 2 is all we have left, but it's 2 on the line. So this is 3 times 2, which is also 6. So this is using the fancy power product where it was b to the m to the n. We got b to the mn. All right. So let's take a look here now at applying this power property. So sometimes it's going to be a little non-obvious how this property can be applied. So our first one here, we have log base 5 of the 5th root of x to the 4th. Why? Why would you do that, Liz? Because the book might give you one of these in the homework. And there's actually just a nice little trick we need to use. So I see the 4, the x to the 4th. Yeah, that would come down as a power, but that 5th root is in the way. So I need a different way to write the 5th root. And if you kind of stretch your brain back, when we were starting to talk about radicals and then cube roots, the way you can type any of these crazy roots on the calculator without madly searching through the catalog is you change them into a fraction. but it's an exponent that's a fraction. So this 5th root of x to the 4th is really x to the 4th to the 1/5 power. Now I can actually think of this as, oh, I have the 1/5 power. Well, that's a power. I said power, and I'm doing a log, so it's power down. So I can bring that 1/5 up front. Power down. So this is now 1/5 as a coefficient in front of the logarithm. So 1/5 of, or 1/5 times log base 5 of x to the 4th now. And guess what? You can do it again. Power down. So now we have 1/5 times 4, but we can actually just multiply those and get 4/5 log base 5 of x. And if for some reason someone had told me what log base 5 of x was, well, then I could just multiply that number by 4/5 and I'd know what log base 5 of the 5th root of x to the 4th is now. So that's the power here as well, is logs take things that were really ugly and make them something that is more crunchable by hand. Now, yes, I know we have calculators. We don't have to do this by hand. We are not landing astronauts on the moon. But again, I want you to appreciate like how ugly some of these things were and how elegantly they managed to use math to simplify them down to more calculable, I guess you could say, or less error proof is what it really came down to. So now the natural log of x to the 3rd, I only got one thing to do here. Power down. This is the same as 3 times the natural log of x. Now the log of 8 here like looks weird. I could type that on the calculator, it's an ugly decimal. So what I want to know here instead is there a way I can rewrite 8 so it has an exponent? That I can do. There's actually a couple of ways we could do it, but typically when we're going to rewrite a larger number, we break it down into its prime numbers, or the prime number factorization, which if you're not sure, just take it to the side. I know it's even. So it is 2 times 4. 4 is the pair of 2's. So our 8 here is the same as 2 to the 3rd. So our log of 8 is the same as the log of 2 to the 3rd. And just like the previous example, power down. So the log of 8 is the same as 3 times the log of 2. And you could crunch both of those on the calculator and see they are indeed the same exact decimal. So the base that the log is of does not have to match the base inside it. If they match, then you get to simplify stuff. But if not, you can still make use of this property. All right, so stop that one.